Hello, everyone. Welcome to the Toronto Machine Learning Society's annual conference. My name is Aarti Malhotra, Ph.D. student at University of Waterloo. I'm glad to be the moderator for today's session. I hope all of you are doing fine. I'm honored to introduce Dr. Nima today. Dr. Nima has a Ph.D. in System and Industrial Engineering with background in applied mathematics. He has held postdoctoral position at UFT, Canada, working on machine learning and operations research projects in collaboration with various industry and service sectors. He was with Bombardier Aerospace before, with focus on ML/OR methods for reliability survival analysis, maintenance, and airline operations optimization. He's currently with Data Science and Analytics Lab at Scotiabank, Toronto, as a senior data scientist. He has more than 40 peer-reviewed articles and book chapters published in top-tier journals and papers at top conferences, as well as a published patent. May I now request Dr. Nima to present trade-off between optimality and explainability and enlighten us. If anyone has any question, please feel free to post in the chat. We will have a Q&A session after the talk. Over to you, Dr. Nima.
Thank you so much, Aarti. Can you hear me?
Yes.
Okay, thank you. Thank you so much for your nice introduction. Hello, everyone. I'm Nima from Scotiabank. This is a joint work with my colleague, Taha Jafar. We are talking about the trade-off between optimality and explainability. So let's start with for now, I turn off my video and then switch on the PowerPoint. Let's give you a very quick background why we are talking about this trade-off and what's the importance of the topic. So you know that the explainability is getting very important now. AI regulation is coming. There is a paper in HBR, Harvard Business Review, that mentioned many governments move to regular AI systems with legal requirements and on fairness, transparency, and explainability. And recently, Europe Union processed strict rules for artificial intelligence based on the New York Times article. So I try to explain everything. That's very hard, but I try to explain everything in the chart I designed. In this chart, the x-axis is a level of risk of the associated field. We are working on it or doing some AI project, ML projects. And the y-axis is the importance of explainability and at the same time high around the machine learning. So low risk field, we have a medium risk field, high risk field. When you're moving on the x-axis, why we say low risk, mid risk, or high risk, that depends on the cost or risk associated with the false alarms. And that's very important. So I had a presentation on ICML 2021 to this year that I emphasized on quantification of false alarms directly into the loss function of any type of machine learning you are using, because this is a reason on how to measure the economic value of machine learning application. That this is a lack of such a quantification at this moment. More specifically for high risk field like a finance, aerospace, healthcare, cybersecurity. Moving on x-axis, the importance of fairness, transparency, and explainability increases exponentially. More specifically, the importance of exogenous variables. For example, in finance, we have contrary to the aerospace and healthcare, we have open systems. That means many exogenous, or in terms of the latent or confounder variables affect the systems. That's why the explainability and transparency getting much more important. So at the same time, there is a marketing hype, more specifically around the low-risk field, like entertainment, gaming, video idea streaming, dating platform, real estate, travel recommendation engines, or whatever. So this marketing hype gives some signals to the market that like singularity point is very close, and no need for human intervention. That's why there is a lot of signal in the market that no need for anymore. We don't need a data science. Just hire AI engineer and just create the pipeline and put everything in the pipeline and just and then run the machine learning or AI platform. So, but this is not the case. My claim is that if you look at the dash line, at the bottom of the chart, this is the explainability power of black box models, BBMs. This is my term, BBMs for black box models. This is the explainability power of BBMs like 10 years ago. So, but we have some progress recently. Recent progress in explainable neural networks, EXNN, Shapley value, causal inference, and many things. Those are less theoretical progress, but more computational progress, highly rely on the data itself and classical statistics and mathematics. But I want to claim that we have much more to do, actually needed to be done. We have to fill a lot of gaps in theoretical gaps in optimization and geometric algebra. And to be honest, we don't have a clear definition of intelligence. So what is intelligence? We are talking always artificial intelligence, but what we are running at this moment, all in deep learning, everything is just classical maths, finding the saddle points, cross-validation, a lot of statistics involved to run the model. And the model needs a lot of data, clean, balanced data to make sure everything's okay. So this is the reason. So another reason is that there is a strong tie between machine learning and statistics. I started with this funny question: if gambling is all probability, why are not the statisticians the richest people? So maybe the one reason is that the statistics and probability theory are not exact science and cannot be fully trusted in high-risk applications. And based on the Bertrand's quote, he's an MIT professor. So he had a talk in University of Toronto years ago. I attended, and he has a beautiful quote that AI/ML is fundamentally rooted in the statistics with the high level of inherent randomness and stochasticity. If you look at this chart created, so you can see a stochasticity and randomness everywhere during the develop of the machine learning, from feature selection, dimension reduction, to model selection requirements, hyperparameter tuning, bootstrapping and cross-validation, initialization of the model and training. All of them, if you look at, there are a lot of stochasticity and randomness in the systems. That's another reason why BBMs, black box model, are not really explainable. So what's the challenge? The challenge is that explainability is a serious concern in high-risk fields. So regardless of the model accuracy, BBMs cannot trust it in high-risk field due to lack of explainability. Let's give you a couple of examples. For example, in healthcare, we have a cancer screening, and you use a black box model like a NLP plus autoencoder. So, and then a mammography picture is flagged as a potential for breast cancer with a high accuracy. But why? The question is why that's happened. Or in finance, you use XGBoost for default prediction. I mean, a client is predicted to default over the next quarter or not approve for a loan with a high accuracy. But why? We cannot explain it sometimes. The accuracy is good, but the model is not explainable. So we have to spend a lot of effort and a lot of statistics to find why. What's the root? What's the main cause of lack of explainability? That's black box model not explainable because structural complexity of the model, like the deep models, ill-defined loose function, you are not the right loose function, or well-defined but complex loose function. You're in the right page for defining the loose function, but your loose function is not is very complex. It's not, for example, non-uniform continuity, non-differentiability, non-convexity, non-linearity, and integrating all of them. We have a big issue currently in the optimization field and theory of optimization is lack of global optimization guarantee. That's the main focus of this presentation. That's why I want to tie this theoretical gap to the explainability. So my claim is that according to no free lunch theorem and above gap, I mean lack of global optimism, there is a trade-off between explainability and optimality at some point. When you want to select the model, you have to make a trade-off between explainability and optimality guarantee. So my main conclusion is that in high-risk fields, that's my concern, a more explainable but less accurate model maybe is better than a less explainable but more accurate model. So, but let's have a clear definition of explainability. So what is explainability? So if you look at the literature, we have a huge literature on explainability at this moment, coming progressively because of the importance of the topic, why the model make a specific prediction outcomes, which feature drive certain predictions, and how and to what extent small changes of the input modify the output. This is many seemingly different questions, but all target at the same things. All this question can be divided to two different type of explainability. Counterfactual explainability or causal explainability or explainability through causality. So counterfactual explainability. So assume that you select a machine learning model, a black box model. I created like a FOGO. So that's going to be any type of black box model. You want to train the model based on having a target, a bunch of the features, and train the model to get the optimal coefficients of the model. So, but after you train the model, there is a shift in data and perturbation. There is change in model parameters, and counterfactual explainability. You want to say how change in the X or any feature or any parameters of the model gonna change the learning coefficients. So that's I simply shows by this differentiating Y in terms of the X1. So other side of the coin is causal explainability. That's not my the concern on the focus of the paper of this presentation. I'm just talking about the counterfactual. But at some point, counterfactual and causal explainability should be two sides of the same coin, and at some point they should verify each other. But this is a missing part in machine learning. We don't have it at this moment. Causal explainability, you choose a causal inference like a Bayesian inference, for example, or any type of conditional probability, and causal inference gives you a direct cyclic graph on how variables affect each other and finally affect the target model. So there is a latent or co-founder maybe that we can find it through the causal inference, but this is not my focus of the presentation. But at some point, counterfactual explainability and causal explainability should explain each other, but we don't have it. So this refers to Rashomon effect. Rashomon effect says that many accurate but different models give incompatible descriptions of the data and thereby varying prediction. And that's one of the key issues that the lack of the machine learning at this point. I mean, we don't have a methodology or any proof, mathematical proof to that counterfactual and causal explainability verify each other at some point. And this is another reason why we cannot explain the model or model or not explainability, or we have a spurious or wrong explainability. I want to tie that to lack of optimality guarantee. So why optimality? Because when you're dealing with each ML model, you're talking about the optimization. You want to define most likely a nonlinear, convex, or in the worst case, a non-convex problem. So optimization is the core of every machine learning model. But learning is a constraint optimization. You want to minimize the loss function error plus soft constraints, or we say penalty term, subject to some hard constraints. Hard constraints is more information or knowledge transfer from expert to the model. So counterfactual explainability is very similar to sensitivity analysis or what if scenario in operational research field or optimization field. So, but global optimal or near global optimal guarantee is the key assumption in sensitivity analysis. So hereafter, I'm showing near global optimal with N-GO or NGO that guaranteeing the global optimal or near global optimal. In convex problem, we have prime and dual problems that the dual and prime problems should have same objective function value at NGO points, and this is the key things, the key objective or the key requirement in sensitive or any type of what if scenario analysis. So the interaction between prime and dual problem is the core for almost all exact algorithms to solve nonlinear problems, like active set methods, Lagrangian relaxation theory, convex relaxation, grid search, and many things. So that's why optimality is very tied to sensitive analysis, and sensitive analysis is actually the same of counterfactual explainability. But about the nature of the problem, as I mentioned, could be convexity. The learning problem could be a nonlinear convex or non-convex problem. A strict convexity, if your problem is a strict convexity, you can guarantee a unique global optimum. Composition of convex function is not convex, like a composition of various layers in deep models, or QCQP, quadratic constraint quadratic programming. That if your objective function is constraint, and your constraint is quadratic and objective function is quadratic, the combination could be a non-convex. Maybe we have a degeneracy problem. We have a multiple NGO points with the same loose function values. If your learning problem is not convex, and non-smooth error surface, more specifically, if you have a L1 norm or lasso, any type of lasso promoted terms, your surface or landscape going to be non-smooth. So the majority of black box model, as you know, are non-parametric, like a deep networks, decision trees, and have a non-linear, non-convex loose surface with many local optimal salad points that's going to be grow exponentially in the number of parameters. And for non-convex problems, NGO theoretical guarantees are weak or non-exist at this moment. That's non-convexity is getting very serious issue in many real-world application of the machine learning and AI. That's non-convexity depends on the application, and there is usually no theoretical risk safety for setting hyperparameters for non-convex problems. So that's why non-convexity and non-linearity for learning problems is very key to many machine learning applications. And if you cannot guarantee the NGO near or global optimums, your explainability could be completely wrong. So as I mentioned, learning is a constraint optimization problem. So because you want to add more knowledge to the model through the generalization for a better generalization and interpretability. For example, we have a group or general sparsity, limited pairwise, multicollinearity, nonlinear transformation, robustness, stable to outlier, statistical significance, and all of them could be as objective or hard constraint or soft constraint in the form of parametric function. So usually learning is not usually the most, inherently learning is a constraint optimization that if you add each of this constraints, that your learning model could be very complicated or mostly a non-linear and non-convex problem. But the optimal point is a misused buzzword in the literature. Sometimes there is a big difference between local and global optimal. Good, sometimes most of the time we are looking for the good solution, but good solution is not enough for explainability. So if you look at this graph, so we have an original loose function, very clean, strict convexity. But when you penalize loose function to give more information and knowledge to the model for learning, you have a more complicated loose function with a lot of local optima, flat minima, and as well as near global optimum, NGO. So But using the current methodology, most of the time we trap in the local optima. That local optima could be completely different or differs completely from real near global optimum from two sides, both structure and performance. If you look at, for example, this dashed blue line is a random selection, and the performance of the model is a difference between your optimal and random selection point. So if you trap in the local optima and your local optima in the future space is far from your near NGO, you have a spurious explanation or wrong explanation on both model performance and solution structure. I'm just showing this very simple clustering examples that the local optimal is completely differs from global optimal, from both structure and performance. So this is another example of optimality and spurious explanation, wrong explanation. For example, you can get the wrong explanation when you change the model parameters. The model parameters, any change in model parameters can be interpreted as a change in the constraints, like this one. So if you have a non-convex objective function over a convex learning structure space, if you change one of the model parameters, the optimal solution, global versus local, could be completely different. Look at this one, guys. So in this case, if I access to the NGO, this is the real change. I mean, using this, I have a small changes in terms of W1, but a significant change in terms of W2. W1, W2 are the coefficient, learning coefficients. So, but if you trap in the local optima, you have a wrong explainability. That this means you have a big change in W1, but very small change in W2. So assume that if W1 is any interaction between XY, between two futures, like X1, X2, this gives you a completely wrong explanation of the learning model. So what's the insights of my presentation for high-risk fields, guys, is instead of training a zoo of complex models, the literature should be focused on theory to guarantee NGO under non-convexity. So advancement in computational algorithms and computer hardware are good, are necessary, but it's not sufficient. More specifically, in high-risk fields, we have to be careful about the model selection phase. We have to focus on less accurate but more explainable models where NGO can be guaranteed as much as possible, like a PCA, SVM, or QCQP. PCA actually is a non-convex problem, but it can be shown that with appropriately chosen a step size, gradient descent method converge globally for PCA. That's the model selection phase. We have to be careful on which model we select. Model development phase, we have to try to understand the structure of loose function and the properties of the optimization landscape, and try to find high quality bounds. This is really is not a statistics, it's more geometric algebra. I think that my concern is that we have to do a lot of things, a lot of development in theory of geometric algebra to understand the landscape and the landscape of the loose function or error function. So given that this discrete problem, like a classification and clustering, lack of NGO is much more complicated. And we have that's another story that is not the scope of this presentation. And spurious explainability could be a serious problem, because spurious explainability is not necessarily due to a wrong model, but maybe due to lack of access to near global optimum. So thank you, everybody. Just that was my MP3 very quick presentation of the trade-off between optimality, and I would be happy to answer your question.
Thank you, Dr. Nima, for the insightful talk. We'll have some Q&A session now. I think first question is from Mehdi. Strength of ML is that the assumptions are often very weak, but due to the nature of, let me read it. Nature
Causal
of
inference, yeah.
causal inference. There are multiple non-provable identifying assumptions.
Assumptions such as, yeah, unquotable
Yeah.
accident, causal inference. Those two don't go together. How do causal inference? So see, that's a good point. So based on my presentation here, Mahdi, so I'm seeing the causal inference as another method, another ML method to explainability. So my point is that if you have that's a Rashomon effect. If you have two accurate model A and model B, at some point these two models should be verify each other, and this is a missing point. I mean, sometimes you have two or three accurate but efficient models, but incompatible description of the model, and therefore incompatible explainability. I'm seeing the causal inference as another machine learning method.
I had a question myself. How do we be sure of explainability when all we are dealing with is randomness?
Oh, that's actually the question. That's the weakness of the current methodology.
Yeah.
So as shown here, so you can see randomness and stochasticity in every step of the machine learning pipeline. You know, so actually we have integrated, or not, we can say exploding. We have an exploding debugging issue because of this problem. Sometimes we cannot debug the problem. Where is the problem coming from? Why a specific prediction happened? So my concern is that one main stream of machine learning theory is going to be focused on reduction of stochasticity and randomness in the pipeline, and access to the global optimum bring the more robustness to machine learning. And then on top of all of this, we can define the real intelligence. So that's why I think that currently the machine learning, there is no actual intelligence, to be honest. The guys, all of us are data scientists and we're working there. There is no actual intelligence. The machine learning at this time is a statistics, a classical maths plus big data structure, big data science. So we cannot. My point is that we cannot we don't have a clean explainability or trustable explainability, because we cannot access to the global optimum at this point, because we don't know we cannot explain the surface of loose function, honestly, you know. So when you develop a very complicated deep learning model, we cannot from the geometric algebra, we cannot explain the surface model. We have no how many how the surfaces, how many local or optimum we have. We have a flat minima, we have a unlimited number of local optimum, or even unlimited number of global optimums. We don't need it. We don't have it, and this is a missing part.
Yeah, thank you. Another question from Rishikesh: is there a way to evaluate explainability? Do we make hypotheses before modeling and see if model meets them?
So I don't. Based on this charts, if you have a, my point is that if you have assume that we have a mode of selection, that's a good model, accurate model, and we have a training that we can access to the NGO global optimum. Therefore, there's going to be, I mean, any change in the any features in the future can explain the target variable. This is, yeah, that's if everything's perfect, you have a perfect model and you have access to global optimum, and you can perfectly explain the model in terms of the counterfactual explainability. That's the focus of my presentation.
Right. Another question: tools, libraries do you use for optimality versus explainability? What are their strengths and limitations? So
at this moment, I don't use. This is actually open question machine learning. This I just brought. This is my claim. There is no specific package. There are many solvers in the market that you can deal with the non-convexity and global optimization. Recently, there is a published paper 2021 in I forgot the name of the journal, that they just classify the global optimality, the global optimization. But there is not that much. The global optimization for non-convexity is not very advanced at this point. It's very specific application based, but we have some method like a convex relaxation approximation, a type of very advanced Lagrangian theory and great search, and as well as evolutionary algorithms or meta heuristics are in the current market are the main methods for non-convexity and global optimum guarantee. But different solvers have different things. Like we have optimization solvers like a Cplex. We have a GRAPH+AI. We have a lot of free Python packages like a Pulp, many things that we can test at the global optimal guarantee.
Okay, thank you. Another question from Saeed. What is the need for accurate explanations? What about rough explanations if the former is not achievable?
Sorry, maybe I missed. Can you say again? Sorry.
Repeat that. What is the need for accurate explanations? What about rough explanations if the former is not achievable? Rough, I think, is like an estimate.
I don't know what. Yeah, but what does it mean by rough? And so my perspective is that if you can in the case of any change in the feature set, if you can predict the behavior of the target variable, is a counterfactual explainability. You've done. I mean, because we want to why the question is why the model make a specific prediction on outcome, which future effects. If everything is okay, you have a perfect model and you have access to the NGO, and then you're done. I mean, it's not very complicated. Maybe the reason for complexity behind the definition of explainability is because of the rational effect. I mean, we have a lot of accurate model with a different description.
Right. Okay. Shrikant has a question. Is there any literature or resources on NGO? I haven't heard that before, he says.
Exactly. Yeah. NGO is a very old topic in operations research, but as Professor Bertrimas mentioned, the reason most of the people never heard about the global optimization or any literature because we are dealing a lot with the statistics and machine learning. So there are huge. If you search for global optimization, you can see a rich literature. But global optimization can be divided to convex for non-convex. For convex, we have a very good one, but for non-convex, they are undergoing discussion that how we can deal with the global optimization for non-convex learning problems.
Right, thank you. Rohan has a question. Traditional models, GLM, with many variables having correlations and interactions, interpretability is difficult. How this issue is tackled in finance?
So in finance, we don't have a magic approach, the same as the machine learning, other things. So as I show in this slide, yeah, we have to add. We can add many as much as possible constraints to hammer the surface, the solution surface, error surface. But for GLM, I don't have at this moment. I don't have idea specific solution. But we don't have a specific solution in finance, so we use the same methodology the other use. Depends on the number of the features and number of the label data. You have to choose your right model.
Right. Okay. I think another question from Anand. What is the best way to make deep learning neural nets resistant to adversarial attacks, given we do not have a measure of what the machine has learned, that is the global optimal or distance from it?
To be honest, I don't know at this moment, so I should refresh my mind. But global optimum could be could be a problem or issue in all deep learning models, because any change in the number of layers or any change in the activation function can generate a very complicated landscape error that the guarantee that make the guarantee the global NGO guarantee very, very difficult. So it doesn't matter what's your architecture. So most of the in the current literature, the stochastic gradient descent is the dominant approach that looking for the saddle points and local, but never guarantee the NGO. For NGO, you have to choose another other methods like a grid search or other types of or try to keep. One of my recommendations is to try to keep your error surface and constraints close to quadratic programming as much as possible, because for most of the 99% of the quadratic programming models, we have a NGO guarantee that the algorithms can guarantee there are algorithms that can guarantee the NGO.
Okay. Question from Daniel. Is there any successful ML algorithm having been deployed in credit risk domain?
Credit risk domain is yes, but it's not the scope of my presentation. So I'm not. I don't remember a specific one, but yeah, there is a literature, but it's not the scope of my presentation.
Okay, thank you. Mehdi has a question. Gold standard in causal inference is clinical trials, but we don't have them, but we have observational data. Then we must assume we have access to all confounders, but again, we don't have access to all confounders. So can't guarantee causal inference, especially individual level. Maybe there's some hope for global, and that also assumes that we have observed all confounders. Do you agree with this?
So let's read the question again. Sorry.
Yeah.
Can you read it again? I can't find it here. Who's
Yeah, it's little on the top.
What was the name?
Mehdi.
A student of ML. This is this one? Or?
Yeah. Says the question is deeper. Gold standard in causal inference is clinical trials. Mehdi, can you rephrase it in a shorter form?
Oh, yeah. Gold standard in causal. So maybe that's to be honest, it's not very related to my presentation, but because I'm not talking about the causal inference explainability, but this is completely your question completely related to causality explainability. But yeah, finding the co-founder is one of the key message or one of the key reasons we are working with the causal inference. It's very open question. Yeah, we because one thing is from causal explainability. One of my open question from causal inference is that how we can estimate the size of the causal networks, including, for example, you have some variables that known variables, but what's the size of the hidden part of the graph? That's open question. So how many confounder we have? So that completely depends on the type of the method you use for causal inference. Let's give you very so
Dr. Your voice is breaking a little bit.
Oh, sorry. Can you hear me?
Yes, it's still breaking a little bit.
You're fine?
No. But with some noise.
Oh, okay.
So
just I try to make it short. This is the summary of literature around the causal inference methods. So one of the issue currently we have is every different type of the causal inference can result in different causal networks and causality graph, and therefore applying different methods can result in different number of co-founder variables. So there are some very strong partnership or strong vendors like Causal Lens. That's a company specifically working on causal inference.
Okay. I had a question on slide 10 in your presentation. You had the learning search space. It seems it would be continuous and infinite, right?
Exactly.
How do you constrain it?
So that's a good question. For example, this constraints W1, W2 are coefficient, learning coefficients, okay? So assume that one of the constraints is that W1, W2 should be greater than 0, yeah? And we have a bunch of other constraints like lasso constraints. Let's assume in a ridge regression or lasso regression, you have a constraint on the number of, on the sparsity, okay? And a sparsity or a smoothness could be another constraint. And therefore you have a closed learning search space. And over this closed learning search space, you try to optimize your loose surface, or loose function, error function. That most likely is going to be non-convex function here. That's a very simple one, you know? Okay, so another type of counter explainability is that what if you change one of your parameters in the model? For example, you change your lasso or ridge constraints in regression, increase by 1, like here. And when you increase by 1 or you change the slope or whatever, you have a change in your constraints, and therefore you want to rerun the model. Okay, if you have access to the global optimum, this is my initial global, and then change to this point. Okay, and that's the right one. I mean, the explainability is that if I change, what happens if you change the parameter of the model, your global optimum going to be, your solution going to be changed like this one. But at the same time, if you do not access to NGO and you trap in the local optimum, you could be completely wrong from explainability, you know? So this says that the red one is the local optimum. This says that if this is the initial one and you change your constraints, this is going to be second, your new point. And this is completely different from this. And you can see if you don't have access to the NGO, your explainability should be completely wrong or non-robust.
Thank you. Is there any other questions from the audience? Just have a couple of minutes left.
Situation is always safe and dependable. I agree in the high risk area. I prefer to use parametric, less accurate but more explainable.
More explainable. But in like critical applications, maybe accuracy is also important.
Exactly. So if you look at my first presentation,
yeah.
That's the same. I mean, the hype around the machine learning in low risk area really negatively affects high risk applications.
Right.
And in this case, finance is my focus because in finance we have a lot of exogenous variables, like Latin profounder, and therefore we have to be very careful when we come with the explainability.
Yep. Okay. Yeah, questions, I think. On behalf of TMLS team and everyone here, I'd like to thank you, Dr. Nima, once again. And I encourage attendees to visit our partner booths to enter in some exciting getaways.
Thank you so much. Thank you, everyone.
Thank you.
Bye.
Bye.